Right, our next speaker is, well, he was here about 30 minutes ago in our video conferencing system. Right now he's not there, maybe he has some technical issues, but that doesn't play such a big role because particularly for these purposes we're always making a pre-recorded video and to avoid the cases that something doesn't work. And so we can play the video right away. Can't welcome him here on the stage. Thomas Boegl is an employee at Roth & Schwarz. He is the director of a department there, and he's doing research on receiver and transmitter architectures. And he submitted a talk about the question on the perfect RF receiver and how it would look like today. So, dear video team, I would like to ask you to play the pre-recorded video.
Hi everybody, welcome to the Software Defined Radio Academy looking to concepts for software-defined receivers. My name is Thomas, I'm Delta Lima 9 Mike Delta Bravo. It's a pleasure for me to be here, and let's go now. I've brought with me a very important question, which is discussed very emotional sometimes on fact, and the question is, what is the best concept for a software-defined radio HF receiver if we had the opportunity to build it with all available technology today? And the question is it direct sampling or is it IF sampling? And so we will have a look to that. This is, by the way, the only slide with text. The other slides are a mix of text and pictures, and I do my best to keep you awake, okay? Let's start. So talking about concepts of receivers always requires to know what the receiver is doing. What is the use case? What is the environment the receiver is used for? And the reason for that is we must be aware that a concept A could be perfect for a use case A, but it may be completely useless for a use case B. So the most important question whenever we are starting to design a concept is, what is it good for? What is the use case? So that means we have to look to use cases because HF receiver have to fulfill a variety of requirements. Sensitivity is very often discussed, but we have to talk about robustness and some other parameters. So that's the reason why key requirements and of RF concepts are based on the use cases, and the architectures are combining specific advantages and disadvantages. And for that, it's absolutely necessary that we look to use cases first, what we will do in the next few slides, okay? So our main use case is quite simple, just receive. So we are receiving weak signals, added antenna, we have the receiver here. But if this would be the complete use case, the job is finished, because in such an environment, for instance, if you have a quiet requirement where the receiver is alone, and we have no noise from externally, no interference from externally. So that's quite easy situation, and we have to say every concept is fine for doing that. So that means there's a reason why we have different concepts, and the reason is quite simple, because the difference between the concepts, direct sampling, IF sampling, and the details behind are based on the ability to still pick up weak signals, but also strong interference may be present and all at the same time. So that's the basis for our use cases we have to look at. So we have to complete this picture by just adding a transmitter close by, which will act as an interferer right now. And now we have to ask questions. How strong are these interferers? So what is the level? What is the frequency difference between receive signal and the interferer? And we have also assumed the quality of the interferer. We will see in the next slides, because the interferer will affect even a perfect HF receiver. And we must be aware what is the wanted signal with the minimum level we want to still be able to pick up in the presence of an interferer. So we have the interferer here, and the interferer signal is falling into the receiver antenna, into the receiver front end in parallel to the wanted signal. So we have to look at the total decoupling between the transmitter output and the receiver input to get an impression how the use case will combine interferers and wanted signals at the end. So we go further with the question, how strong are the interference? And I have brought with me two examples, just to give you a rough order of magnitude of parameters we have to take into account. So the first example is based on military scenarios, which we have, for instance, in Navy ships and also in coastal stations. So the frequency offset, which means the difference in frequency between the wanted signal and the interferer signal, is 10%, plus minus a few percent, just depending on the installation, but 10% is a good value to calculate for. The antenna decoupling is quite low because we have a lot of big antennas close by, small distances between the antennas. So 15 dB is a quite nice typical value. We can have even a bit less or a bit more, but 15 dB is a good order, a rough order of magnitude. And the transmit power typically is in the order of 1 kilowatt. We have a bit more, a bit less. We have some losses from antenna tuning units, but 1 kilowatt is a quite good value to calculate with. The second example is derived from radio amateur installations like in field days. And here we have first smaller frequency offsets. For instance, if we are in the same amateur radio band, for instance, CW on the low side of the band and single sideband voice in the higher side of the band, so we have roughly 100K difference. If we go to the next amateur band, either above or below, we have at least 10% and more. So the main difference, additional to the frequency offset, is the difference in levels. So we have not only a bigger antenna decoupling, some dBs more, in this case roughly 10 dB more, we have also normally less output power in average. We might have more, we might have less, but this is a nice average value. So that means these two scenarios are roughly different by 15 to 20 dB. But we have to also answer the question about the quality of the interferers. And here I brought with me values, and don't be surprised. These values can be provided by high-end equipment today, but mainly only in military installations where we have a special designed transmitters with co-side filters inside. So we have to calculate these values, which is roughly minus 150 dBc per hertz at a frequency offset at 100 kilohertz. And far out, we have up to 180 dBc per hertz, which is extremely good in frequency offset of 10%. So these values are normally not provided by amateur radio equipment, but military equipment, these values are usual, and the outer value is realized by special co-side filters and a special level plan designed for the transmitter. And by the way, the filters used for getting the spectrum clean is also used as a pre-select in the receiver case, because if you can imagine, then if we are changing the direction in a transceiver configuration, then it will be good to have this high quality filter inside in the transmitter chain also used as a receiver front end. Okay, let's look to the spectrum situation and ask the same question and see how it looks like. So here we have our picture again with the receiver and the transmitter. So the transmitter is represented mainly by three values. One is the maximum output value, which is on top here. Then the frequency offset here, in this example, 10%. And the sideband noise. I'm just taking sideband noise, no discrete spurs, and the sideband noise may fall into the receive channel. The receive channel is represented here by the green IF filter. And let's just check the rough order of magnitude we have. So if we say we have this high-end transmitter providing 180 dBc per hertz at 10%, and let's assume we have, for instance, 300 hertz CW filter, then we have a difference in level here of 155 dB, which is an extreme high value. And you can see it only makes sense if the transmitter is so clean as seen in this picture. So that means if we have an interferer which is clean, then the interferer can come even closer, and the noise is lower, then the interferer can even come higher. So that means there's a relation between the spectral purity of the transmitter and how close the transmitter can come to us before he starts to reduce our sensitivity based on either saturation of front ends or by transmitter noise falling into our receiver passband. So that means, as a consequence, a clean interferer can come closer. And if the interferer is less clean, he is overlapping our noise in our receive channel, we must go down with the levels, or we have to accept that the receiver sensitivity is just reduced based on the noise coming from external. So if we have a clean interferer, that it may be allowed to go into level areas where it is significantly higher than the wanted signal. And what we have to do now is we have to bring all this in what I call the operating window of an A to D converter. So let's imagine this is a direct sampling receiver, and it wants to sample the complete spectrum from the HF band up to 30 megs. Then the operating window of the A to D converter, which is a frequency range and it's a level range, just shown with this colored window. This can be pointed to the spectrum at the antenna level. And if we have the critical situation that we have a strong interferer exceeding this window, in that case, if we still want to receive broadband, we have no other chance than just shift the window up, because we want to have this signal lower than the maximum allowed level at the A to D converter, but in that case we are losing sensitivity. But our goal, building up a good receiver, is to have all signals within the operating window of the A to D converter. And that means if we do not have an A to D converter which is providing this wide gap in level, and which is not the case today, so everything beyond 100 dB normally is not possible with a direct sampling without preselectors. So in that case, we must insert some kind of selectivity. So that means our concept will now use a preselector filter. And now let's look a bit more in detail to the preselector and what this thing is doing for our concept. So here we have our spectrum again. And now I'm placing the operating window of the ATC just side by side. So we have here the strong interferer. Here we have a weak wanted signal. And now we have to suppress this strong interferer by just introducing a selectivity. In this case, the blue curve is representing a bandpass filter, which is providing a missing selectivity and suppression. And this will bring now this red interferer into the operating window of the A to D converter. So we have only green signals left. So that means if we are offering this spectrum to the analog to digital converter, it will be fine. Looking to the spectrum domain at the receiver concept, so we have a preselector here represented with this bandpass filter, and the preselector is reducing the interferer level here by some dBs, some 10 dBs, and the interferer is now looking like this. But the interferer is still providing noise into our receive channel. So that means we can help the receiver with a look to the robustness by suppressing interferers, but the interferer spectrum purity is still as relevant as before, as without preselector. So let's see where we are in the moment. Let's hold in for a moment. So with a clean transmitter, we can come closer. That's sure. The question is, how close can we go? And we must be aware that those persons and organizations who are operating this transmitter signal has a responsibility to keep received channels clean. So if we are the interferer, for instance, during field days, we have to do our best to keep our transmit signal as clean as possible if we have the chance to do so. So that means when we are talking about receiver concepts, we are finally talking about concepts for transmitter and receiver in the same time. So it's finally a transceiver discussion. And the receiver part is only one part of it. And the transmitter is one part of it because we are normally double using some resources like filters. So the question is, how close can we go? And the answer is quite simple. We can go as close as we are still able to bring the interferer into the operating window of the ADC. So if the interferer is coming close, which is doing right now, then we need a better preselector. So it's quite simple. So that means as long as we have a sufficient suppression here, then we are still going with a direct sampling concept. But from a certain point inward, we must be aware that the preselector will not be able to provide a sufficient selectivity without any other implications. So that means if we need more selectivity beyond a certain value, we must insert an IF frequency where we can place this additional selectivity. So the IF sampling concept is starting when the selectivity of the direct sampling concept is not sufficient anymore to support the given use case. So the question is still not answered. What is better? IF sampling or direct sampling? What do you think? I say the winner is both are fine. Surprise. Because it's depending on the use case, and as long as the total selectivity of the concept is fine to suppress all interferers sufficiently enough, then the direct sampling concept is fine. So let's look to the operating window again and now place different preselectors. So represented by these three different curves. The green one, let's say it's easy to be achieved. The yellow, probably a bit harder, but okay. And from the red one on, we have to think about changing the concept from a direct sampling to an IF sampling concept. But there's no hard limit in between. Because you can imagine if you have now a better A to D converter, which can provide 10 dB, 20 dB more dynamic range. In that case, the preselector can remain the same and we can come closer. So there is no hard limit. It's a floating decision, just depending on the situation we have to face with interference in frequency offset and in levels. And this is represented by this graph and says just simple. We are starting with a direct sampling concept. And if the level of the interferer is increasing, and the difference in level between the wanted signals and the interference signals is increased, then we are heading an IF sampling concept. Also, when the difference in frequency between interferers and wanted signals is decreased, so that means coming closer and going higher, then we are heading an IF sampling concept. So there's a floating threshold, and we have to take into account many parameters, and we have to know the use cases, but both concepts are fine. The direct sampling concept is okay up to a certain point, and from that on, we have to go with IF sampling concept, providing the missing suppression to go with higher and closer interferers. And if we have made the decision going for an IF sampling concept already, in that case, we can also relax the quality of the A to D converter, which says we can use a cheaper one, because anyway, we have now sufficient selectivity distributed to the preselector and to the IF filters. So that means we can relax the complete receiver concept. So IF sampling and direct sampling is also a question of costs for the complete receiver. So it's not only a technical effect, it's also an effect of costs. Now let's build up our receiver, and a good receiver normally has to provide the capability monitoring a wideband spectrum, for instance, a waterfall diagram, a spectrum monitoring signal, and receiving narrowband signals in a critical use case. So finally, we combine two concepts. This is shown by this picture, and high-end receivers are using two different paths already. And the wideband path, it's for sure a direct sampling concept, because it's the only way to sample the wide bandwidths, because in that case, an IF sampling concept would not help so much. The narrowband path may be different, but not necessarily. It may be the same concept if the use case is okay for that, but it may have different settings. So even in cases where we have the same block diagram, for instance, gain control may be different, filter settings, timings may be different. So in ham receivers, in high-end ham receivers, we have both concepts available, which is a really good choice. Now let's look into the blocks. Now, not being shocked, please. So I've put both blocks close by, side by side, just to see the difference. So both blocks are ending with an A to D converter, and the green block is a digital signal processing block. Both blocks have preselectors. So preselectors for a narrowband receivers are best using bandpass filters, probably cascaded with an amplifier in between, while a wideband receiver is best for combining high-pass, low-pass filters, just to keep the remaining bandwidth as high as possible. It's also a good choice to use notch filters, because these notch filters can be tuned on discrete interferer signals and can suppress this interferer selective and remain the rest of the bandwidth as high as possible to give us a chance to monitor the rest of the spectrum. And by the way, signal processing algorithms are quite nice and able to tune the notches automatically, even in cases when the A to D converter is slightly overdriven. So that means we can open up the front-end preselected bandwidth if we have some notches. So the remaining difference is a RF synthesizer with low noise mixing, probably upward for the HF receiver 70 max or something like this. And then we have IF filters, probably we have different filters, different in bandwidths, just to ensure that the analog to digital converter sees only the required spectrum. We keep it as close as possible and as wide as necessary. And we have the choice to use different IF frequency values like 69 or 70, a bit more, a bit less, just to avoid any mixing products, just depending on the selected frequency for the complete receiver path. So the difference is mixing and filters, and the difference is also seen in the data sheet. And this is the last slide now, looking to the data sheet, what we can expect if we are building up these concepts with the best components available. So if we have no interferers present, then we have just a difference in selectivity given by noise factors. I just assuming a bit higher noise factor for the narrowband pass caused by a high quality preselector and some cascaded stages, which will result in a bit higher noise factor. The wideband receiver can have a slightly less noise factor due to some simpler preselector filters. So the difference in the basic selectivity, basic sensitivity is just the difference in noise factor, but the capability of operating different levels between interferers and wanted signal is significant here. You can see, so the IF sampling concept can go up to 150 dB, roughly in this order of magnitude, while the direct sampling receiver, if the interferer is present at the A to D converter, is roughly in the order of 95%. Probably a few dB more, a bit less, but this is a rough order of magnitude. And if no interferer is present, so both will have a really nice sensitivity, 0.1 microvolt or even a bit less. The difference is shown if we have the use cases. And here we have our 3 use cases from the previous slides again. The military use case is use case 1. 1 kilowatt, 180 dBc per hertz in 10% offset and 50 dB antenna decoupling. And here we have our 10% for the amateur radios and our 100 kilohertz for the amateur radios, both 150 watts and 25 dB. And here you see the difference in selectivity. So pass 1 is the wideband pass, you see here on the left side, and pass 2 is a narrowband pass. And you see here with a high offset, then we can assume that the preselector of the wideband configuration, the wideband receiver direct sampler, is sufficiently good. So we have the same sensitivity. So the difference is if the interferer is coming closer. So that means here with the preselector and here without preselector, you see the significant difference. And here we have still a very nice sensitivity for the narrowband receiver. And here in that case, even a nice sensitivity when the the interferer is very close. So the difference is just the remaining sensitivity in the presence of strong interference. And we have to check our own personal use case, our own installation, where we want to be, and then decide which concept is best. So that's it. Thanks for watching. Many thanks for your attention. Now I'm open for questions.
Okay, Thomas, you're here. Technical problems are solved. That's good. So now it's up to the audience to raise questions. Do you have any questions?
Thank you, Chairman, and good afternoon, everybody. I'm Sven, OZ7S, and I remember a presentation at Friedrichshafen 3 years ago. It was in 2019 about the same subject, and I guess that the one of the conclusions was that was what could be the determining factor between using a wideband receiver, direct sampling at the RF, or a Zwischen frequency would be something like the phase noise characteristics of the oscillators in the receiver. Could you elaborate a little bit on that, please?
Thanks for the question. So phase noise is essential for all concepts because phase noise in a direct sampling receiver is also responsible for desensitization, and then going into the A to D converter, and in the mixing concept it's responsible for reciprocally mixing into the IF. So extremely good phase noise for either the clock of the ADC or the equivalent signal, which is the local oscillator for the IF sampling concept, is the same. We need a very high phase noise quality in all concepts.
Answer this your question?
Thank you.
Okay. Any question more?
Yes, are there any improvements by linearization post ADC, or maybe using things like dithering before the ADC, or is it not needed or not needed anymore?
The problem is quite simple because we have to go into the A to D converter without any compression. Otherwise, the signal processing algorithms after that are problematic. But there are some analog mechanisms which can suppress interferers, like interference cancellation systems, but these are very complex and only suitable in some special installations. So in that case, I rely on a good RF front end between the A to D converter, linear, no extra mechanisms, good phase noise, high intercept point levels, and then go into the A to D converter.
Hello, I have questions for my understanding. For the direct sampling, you have no oscillator normally, only for the IF concept, or is it right?
For the IF
you
sampling,
don't need a mixer.
What? I don't understand.
So
Thomas, go ahead.
yeah, so in both concepts, you need an oscillator. For the direct sampling concept, this oscillator is just the clock oscillator for the A to D converter. And for the IF sampling concept, it's the local oscillator mixing from the RF domain into IF domain. But the importance for the quality for both concepts is exactly the same.
Okay, thank you.
Isn't it true that that a numerical IQ mixer is much better in respect of image rejection compared to an analog one? So doesn't have a direct SDR, so to say, always have this advantage over subsampling or IF system?
Just for clarification, do you mean a zero IF concept,
Yes.
mixing down to the baseband with an IQ modulator cell? Is this the part of the question?
Yes.
Okay, I have some experience with this circuitries, and they have also some non-linearities, and they have some mixing problems in the same behavior if the interferer levels are very high compared to the wanted signal. Phase noise requirements is exactly the same. So at the end, all those concepts are limited by the analog performance of the key components. And for the zero IF mixer, it's the linearity of the mixer cell at the beginning. At the end, it doesn't help because without the pre-selector, also this mixer cell is overdriven. It goes into non-linearity. So problems are different, but with the same importance.
Okay, so we're at the end of the slot. Thomas, thank you very much for your contribution. Very interesting talk, and you see the interaction from the audience is really good. Thanks a lot. Thanks for contributing. Thanks for coming in. And yeah, that's it. Thank you very much.
Okay.
Thank you very much for the
as
invitation.
well.